In 7.5, day 2, we're talking about linear programming. We're jumping off of a problem that we started yesterday, and that's the canoe trip, the food for the canoe trip. And so yesterday what we did was we determined some inequalities that will allow us to meet the minimum daily requirements for the nutrition on this canoe trip. Now what we're going to do today is something that represents linear programming. And with linear programming, we are looking to either maximize or minimize a certain quantity throughout this process. Now, the thing that we're trying to maximize or minimize here is the weight. We want to provide the minimum daily requirements while also having the least possible weight in the pack for these food items. The other piece of information, the one that we didn't really talk about much the other day, was this one down here. Is that each food bar weighs 65 grams and each drink carton weighs 118 grams. There isn't a limit as far as how much weight we can carry. We just want to get this to be as little as possible, and so that's why we're going to use linear programming. So if you'll remember from yesterday, we graphed the inequalities, and we found for fat, carbs, and protein that we have this region as our possible values. Now we call this our feasible region. I don't know if I mentioned that yesterday. This is our feasible region, and so any possible solution to this problem is going to come from that region. Now the thing with linear programming is that we want to choose the best points. We're going to choose the one in this case that will have the least amount of weight, and the one trick is that we're going to only choose corner points. So we look at that feasible region and we just take a look at the corner points. Those are going to be, according to linear programming, that's what's going to make the optimal solution in this case. So we pick those corner points. We've got just some nice values here, 0, 14, 5, 6, 11, 1, which makes sense because we're talking about drink cartons and food bars. We're probably not going to have fractions of those, although this last one down here, just to make sure that this one isn't the minimum, I'm going to include that as well, even though it doesn't make as much sense as the other corner points. So one thing we need to know about this is that, like I mentioned, that each food bar weighs 65 grams and each drink carton weighs 118 grams. This is going to make up what we call our objective function. So our objective function is just some quantity that we want to just see about either making as little as possible or making it maximum if possible. In this case, we'll call it W for weight, and we want to make this as small as possible. We pick the corner points. As I mentioned, we're going to only do corner points when we're looking at that feasible region, and then we're just going to plug them into our objective function. So here again are all those corner points that we found from this graph. I'm going to take those corner points now and I'm going to plug them into this function W. And if I do that, what we will find out is that we get these values. So again, that formula, just for your reference, was W equals 65x plus 118y. So for instance, at the point 0, 14, we're just plugging in 0 for x, 14 for y. We find out that the weight is a total of 1652 grams. And we do that for each of the other points. Now we just take a look at all of them and notice that 833 is the minimum. It's the least value of all of these. So really you're just plugging in every corner point you have and picking the one that you like the best. In this case, that happens to be the minimum. Now I also mentioned about that one that was a fraction number there. It's good that that didn't work because even though that's close to the minimum number, it's not quite as small as 833. So that's the conclusion we come to then, is that if we are at the point 11.1, that means that we are going to take 11 food bars and 1 drink carton per day.